Many thanks. Yes, we have the honor to do the first presentation. The title of our project is Parabolic Maximal Regularity and the Kato square root property. So first I want to present our team. So Manuel will start. Manuel is from the University of Ulm in Germany. Then the next talk is by Vincenzo. He is at the University of Salerno in Italy. The third talk is by Azam. She is at the University of Poznan in Poland. And the final talk, no, the last, but so the fourth talk is by Henning. He is at the University of Karlsruhe in Germany. And then I will give some concluding remark. My name is Wolfgang Arendt. I'm at the University of Ulm. I was somehow one of the founders of this ESEM, so I've seen lot of ESEMs, and it is true. It's a very big family over the world. Now, Henning will start, and the title of his talk is Semigroups, because, you know, there were not enough semigroups so far. So we will start right with semigroups.
Okay. Yeah. Okay, so the title of my talk, I think, was decided upon in the last 10 seconds. But anyway, so it's true, I'm going to tell you a little bit about semigroups, but basically the goal of this little introduction is to link the contents of the lectures of this ESEM somehow to what we're doing in this little project, to somehow show you how the Kato square root property and parabolic maximal regularity are related. Okay, so let me just give you a brief overview of the setup of what we're going to talk about now. So, okay, I'm going to do this on this smaller board because it stays for the remainder. So we're always considering a Hennenfent triple of Hilbert spaces. So V is densely embedded into H, which you can then naturally identify with V prime again. So we also did this in the lectures. And then we consider a bounded and coercive sesquilinear form on V. So this is right. And so we also did this, I think, in lecture 2 in this ISEM. And then we also, in the ISEM, considered the associated operator to this sesquilinear form. So usually you denote this with a curly A. This is a linear operator from V into V prime. It's the associated operator to the form. And you can easily define it actually by saying that AU acting on V, for U and V in big V, is simply the form evaluated in U and V. And since we have a bounded and coercive form, actually this A is then usually called the Lex-Milgram operator, and the Lex-Milgram theorem immediately tells you that it's going to be an isomorphism in this case. Okay, now the thing that Wolfgang already mentioned, semigroups play a role in our project. So let me just briefly mention, this is not from the ISEM, but this is a fact. Maybe I'm mentioning this over here. Then minus A, which is still an operator, generates a semigroup actually. A C0 semigroup on V prime. This is a fact which does not follow immediately from the things we did in the ISEM, but it's still interesting. So minus A, of course, you can see as an operator on V prime if you simply identify V as a subspace of V prime by this Hennenfent triple. And this semigroup we will denote by e to the minus at. Then there's another natural operator that you can associate with this sesquilinear form. This we also did in the ESEM, and this is basically the restriction or the part of curly A in H. So this we call then script A, and its domain will be given by simply those U in V such that AU, which is an element of V prime, but since we associate or identify H as a subspace of V prime, we can simply also just say those U in V such that AU is in H. And then it's natural to say that AU in this case is just AU. Okay, and now actually a result from the ESEM tells you that minus A generates a C0 semigroup in H now. Which we denote by e to the minus at. And this is also a fact. These two semigroups are related by restriction, so this you can just get by restricting this semigroup to H. Okay. Now I want to briefly come to an important theorem, which we only can state in this presentation because a proof of it is too involved for the time we have, but it's so-called trace theorem. And this already gives you an important link between the Kato square root property and parabolic maximal regularity, but this link will be even more obvious when I state the next theorem. But here we see one of the very important actors in the Kato square root property, the domain of the square root of A, defined just via the functional calculus that we learned about in the lectures. And now comes an important observation. This is also a very deep fact. So A has a bounded H infinity calculus. This we also learned in the ESEM. And this fact is very closely related to the observation that you can write the domain of the square root of A as a complex interpolation space. So this is a deep theorem. Of course, you have to prove this. Sadly, we don't have time for it today. But you can write this as the complex interpolation space between H and the domain of A. And now you can also get more involved with interpolation theory and see that this is actually the same as the real interpolation space in this case, which you can define via the trace method. And then you can also see that this is just the same as psi evaluated at 0, where psi is in H1 of, say, 0, 1 with values in H, intersected with L2 of 0, 1 with values in the domain of A. We just take this operator again. So this gives you the interpolation space between H and the domain of A. Okay, so you somehow see that the domain of the square root of A has something to do with trace spaces in time of these spaces which usually appear in parabolic maximal regularity. Okay, so next I want to mention a theorem which then makes use of this trace theorem and basically gives you the solution or an answer to the question whether one has maximal regularity in H for the parabolic problem, which comes from this operator, minus A, that we've just defined from the form little a. And basically, you can prove the following. Again, we have to accept this as a fact, just to see what the setup is in the autonomous case. So we consider a U0 in H and an F in L2 of 0, 1, and H. And then I want to characterize a statement, namely that there exists a solution U in H1 of 0, 1 with values in H, intersected L2, 0, 1, and yeah, here we can take the domain of A. Right, so exactly in this space where we take the trace to get to the domain of a to the half, solving the Cauchy problem, where here we have u prime of t plus a u of t equals f of t, this in L2 of 0, 1 domain of a, L2 0, 1 of h, and then we want that u of 0 is just u0. Right, and this is then the case if and only if u0 is in this trace space. This is just the parabolic maximal regularity result. So if and only if u0 is in the domain of the square root of a. So you can see understanding the domain of the square root of a is really crucial in determining the right space of initial data for parabolic maximal regularity, essentially. And this already gives you the connection, right? So understanding the domain of the square root is crucial in order to gain better understanding of such parabolic problems. Okay, now I want to close with an example which somehow motivates the rest of this talk. So in the rest of this talk, we don't just consider forms which are autonomous or such problems which are autonomous, but the A now may also depend on T. And I also want to motivate why it is really nice to have the domain of A here as the space. So why this actually gives you some maybe more information about the solution U. And this we do in the following example, where we essentially consider one-dimensional elliptic operators with Neumann boundary conditions. So 1D elliptic operators with Neumann boundary. And in this setting, let us just choose the spaces appropriately. So first we consider H to just be the L2 space on the interval 0, 1. Then V will be H1. So similar setup as in the ISM so far. And we consider an M, which is in C1 of 0, infinity. This will be time. So here we already get a time dependence times the interval 0, 1. And we suppose that M is always greater than or equal to some constant delta, which is positive. So this is uniformly where M is defined. So M is real valued. And then we define a form in this sense, but now this form also depends on time, because the M depends on time. So A of t, u, and v will be defined as the integral from 0 to 1, m of tx, and then u prime of x, v prime of x, bar, if we take it complex valued dx. Now it's easy to see that for each fixed t, a of t dot dot is going to be a bounded and coercive form on v. So we also get associated operators, or at least an associated operator for each fixed time t, a of t in L of v, v prime, just by the same definition as to the left. Okay. Now comes the interesting part, really. Now we try to better understand what the domain of stripped A of t is. And it's a very easy exercise to, in this case, simply compute that the domain of stripped A of t is the set of all u now in H2. So if you are in the domain of stripped A, you already have more regularity actually. You're an H2 function on 0, 1. So this is nice about script A. You have more regularity. And you also get the Neumann boundary conditions. U prime of 0 equals U prime of 1 equals 0. Because basically, in order to be in this domain, you must be able to integrate by parts here. And in order to be able to integrate by parts, the boundary terms have to disappear. And this then just becomes part of the domain of A of t. And you can then also easily say what A of t of u is. So this is not the definition. This you can compute to be minus m of t u prime prime. right? So it's this elliptic operator which is induced by m of t. Okay, and the goal is then to solve this problem. So u prime of t plus a of t, u of t equals f. With an f that is in L2 of 0, 1, say, with values in h. So L2 in time and space. And with u0 in v. And some solution u in the maximal regularity space. So that's what we want to achieve. 0, 1, h intersected with L2 of 0, 1 and the domain of A. Well, yeah. Let's also just put this here. And if you have this regularity, then from the equation you can immediately see that u of t will also have to be in the domain of a of t for almost every time t. And then you already get that u of t satisfies the Neumann boundary conditions and has this additional space regularity for almost every time. And therefore, this problem is actually the more interesting one, right? If you compare it to the Cauchy problem, which you can pose for the operator script A. So all right. Now, what do we already understand from theorem 1? If the m is constant in time t, right? So if actually we don't have a non-autonomous problem, so if you just ignore this t here, then the theorem 1 already gives you a criterion for when this is satisfied, right? So whenever the u0 is in the domain of the square root of a, then you can... Sorry? Well, d of a now depends, yeah, okay. Depends on, well, it doesn't actually depend on t. Okay, yeah, I can write, this is fine. So this is actually what we would like to achieve here, that's true. Yeah, so if it isn't a t-dependent problem, if m doesn't depend on t, that I mean, then this immediately gives you a solution for u0 in the domain of a to the half. And we actually know what the domain of a to the half is. In this case, it would just be v again, because we have a symmetric form. And then the parabolic maximal regularity is understood. Now the question we would like to answer in this project is what happens if you have this non-autonomous problem? So what happens if you have the t there? And the next 3 talks will elaborate on this. So the first talk by Vincenzo will be about maximal regularity for the Cauchy problem in v prime. So basically, not if you have the operator stripped A here, but curly A. This is the first step, of course. Then the goal is, if you have this solution, does the solution actually have more regularity? Does it satisfy this? Then in talk 2 by Assam, we will see that this is not the case in general. So there are counterexamples actually, which are closely related to counterexamples of the Kato square root property. This is really nice for this ESIM, of course, to see this relation. But in talk 3 by Henning, finally, we will see a positive result. So if the form has some regularity in T, then actually this maximal regularity in H can be proven. Okay, so let's start with the talks.
So thank you, Mario, for the introduction. As he said, we will deal for positive result for maximal regularity in the bigger space V prime for evolution equation governed by form. In particular, we will deal with the non-autonomous form. So this is a map as before, but we have to add a time dependence between 0 and capital T, which is a fixed real positive number, which we require to be sesquilinear in every time, measurable, bounded, in particular V bounded, and coercive. And as usual, we can associate to this form an operator, a bounded operator, which in this case will be a time-dependent operator curl A, which is bounded from V to V star. And the relationship between the form and the operator is the classical one in every time t between 0 and capital T. So the result that I want to show is this one. So we have a well-positioned result for this evolution equation, in particular this non-autonomous inhomogeneous Cauchy problem, where the initial value u0 is in H, the datum f is into L2 with value in V star. Then we want to prove that there exists a unique solution in this space, which is the maximal regularity space. Here is H1 with value in V star. So I remark that if U is in this space, all the terms of our equation are in the same space, which is L2 with value in V star. And this is why we call maximal regularity. So I'll prove this result. Let's have a quick look to the autonomous case, where we need a weak formulation of our problem. And then the Lax-Milgram lemma will give us the existence and the uniqueness of the solution. So here we will need a weak formulation of our problem, non-autonomous problem, and we will replace the work of Lax-Milgram lemma by the Lyon representation theorem, which is a more general result than the Lax-Milgram, because we will deal with a Hilbert space, a sesquilinear form defined on the products of a Hilbert space and on a normal space. So W is just a normal space which is embedded in V, or a pre-Hilbert space, while in the Lax-Milgram lemma we have a sesquilinear form defined in the product of two Hilbert spaces. And here we will require on the sesquilinear form the continuity with respect to the first variable, while on the other variable we don't have any continuity assumption, and the coercivity. So this make more general in the application, because if we have only a normal space, and this means that a class of more bigger class of functions are allowed to be in the space W star. And then we'll say this theorem that there exists a vector V, U in V, such that we can represent the action of L by the sesquilinear form. And I want to stress also that this is also an existence result, while the Lax-Milgram lemma is give the uniqueness. But if you add some further assumption on the sesquilinear form, a sort of injectivity in the first variable, you can also obtain the uniqueness. And this lemma gives also a bound of U by the norm of the capital L, the functional in W star. So the proof will rely on the very important fact that every Hilbert space is a reflexive space. Let's see why. So we construct this operator T from W to V prime, that for every W associated with the sesquilinear form with W is fixed. And by assumption on the sesquilinear form, this is an element of V prime. Then the other assumption on the sesquilinear form is the coercivity, which gives us this kind of inequality, which tells us basically that T is injective, because if TW is 0, then we have also W is 0. So if T is injective, we can consider T to the minus 1, defined on the image of W with value in W. And this inequality gives also us this boundedness of T minus 1. So I can consider this operator composed by L. L is the element of W star, so it's an anti-linear functional. So this composition is a linear functional which goes from TW to K, which can be R or C. With the inequality that we see before, give us also this a priori bound, which allow us to extend this our operator, this functional, to an element L of V prime prime, because it's defined on V prime and it's also bounded by this inequality with this bound of the norm. And now we have to use the reflexivity of the space V to say that the classical canonical injection is a surjective map. So if L is an element of V prime prime, there exists a U in V such that the action of L on V prime, which V prime is an element of capital V prime, is equal to the action of V prime on U, where U is this element in V. And this canonical injection is also an isometry map, so the norm of this element U in V is the same as the norm of the L in the dual in the V dual space, which is bounded by the norm of L in W star. So we obtained the a priori bound, and we only left to see that we can represent this the action of this functional by the sesquilinear form. So we pick W in W, so we can see the identity here as t minus 1 composed by t. So this is exactly the action of L on TW. And by the surjectivity, this is TW applied to U. And by definition of TW, if I apply TW of U is exactly the sesquilinear form evaluated in UW. So we have that the theorem L of W is equal to the sesquilinear form evaluated in U and W. And now to prove the well-Posner result by Lyons, our aim is exactly to use this representation theorem. But first we need to see how it looks like our weak formulation of our problem. So from now on, by simplicity, I pick U naught equal to 0, but this is always still true if I pick every U naught in H. And this makes sense in H because the maximal regularity space is embedded in the continuous function with value in H. So the initial value U0 equal to U naught in H makes sense. But from now on, I put U naught equal to 0. So one can prove that if U is into maximal regularity space and is a solution of our still inhomogeneous problem, then this is equivalent to this integral equation where we see that appear the sesquilinear form associated to the operator A, cur A. And of course, on the right-hand side, we have appear F, which is the inhomogeneous data. So, of course, we want to prove by Lyon's theorem, we will have that this is true. And then by this weak equivalence, we will have that U is a solution in the maximal regularity space of our problem. So let's recall the main theorem that we want to prove. So we pick an F in this space, L2 with value in V star. In this case, U0 is 0. Anyway, we have to put in H. Then we want to prove that there exists a unique U in the maximal regularity space. So I remember L2 with value in V and H1 with value in V star. So we are in the bigger space, V star, such that it's a solution for every time. And in particular, the following estimates hold true, where if you deal with an U naught here, you have also a term here, which is the norm of U naught, which tell us basically that the operator, which associated the initial data to the solution, is bounded. And for proving this result, we want to, in particular, we want to prove the existence part of this this theorem. We want to use the Lyon representation theorem. So we have to consider an Hilbert space, a pre-Hilbert space, consider a sesquilinear form defined on this product, and then fix an anti-linear functional in the W star, and then the Lyon representation theorem will give us the solution. So as V space, I chose L2 with value in V with this norm, so it's an Hilbert space. While on W, I will, for not make confusion, I will call this curve V. And as curve W, I chose this tensor product space, which basically is a linear combination of these functions, which are cis infinity in time and in space are in V. And on this space, I chose this norm, which come from an inner product, so this is an Hilbert space. In particular, this alpha here is exactly the coercivity constant of the form A that is associated to our operator. Because I remember we are dealing with the evolution equation governed by form. So our operator is associated to a coercive form with constant alpha, and I put here in the norm of W exactly the same alpha which appear here. The first thing to notice is this pre-Hilbert space have to be embedded in the other space V, and this is true by construction, and also we have the continuity of the embedding here by this simply inequality which come from here. Now we have to choose the sesquilinear form. So the sesquilinear form is basically the left-hand side of the weak formulation where appear the sesquilinear form associated to A. And here is what is missing is W of t. So for this form, we have to prove the two assumptions of Lyon representation theorem. So basically the boundedness with respect to the first variable in the Hilbert space and the coercivity. So for the boundedness in the first variable, we just need to use Cauchy-Schwarz inequality and the boundedness of the sesquilinear form A. Because we appear exactly the constant, this can be bounded by a constant M by the product of the two norms in V. And after that, it's just computation with the Cauchy-Schwarz inequality. While for the coercivity of the form A is not enough because we have to deal with this first term. So for the second term, we will use, of course, the coercivity of A, but here we need to do something more. So we observe that the function W is in time dependence cis infinity. So this square norm in H is cis infinity. I can compute this time derivative, which is exactly 2 times the real part of this inner product, thanks to the sesquilinearity of the inner product of H. Now I take an integral between 0 and capital T here on both sides, and I notice that W have support inside 0T with T is not included. So this means that we are sure that W in T is equal to 0. So here this term does disappear, and this integral, which is exactly what we want to know about that, is exactly 1/2 of the norm in W0 squared. So now we can deal with both terms of our sesquilinear form. If we want to prove the coercivity, just evaluate the real part in WW. So the first term is exactly what we just proved, which is exactly 1/2 of the norm of W in 0 squared. And here, as I said before, appear the sesquilinearity, the coercivity of the form A. So what we have here is exactly what we chose as a norm of curl W. So this means that the form is coercive. So for the sesquilinear form, we have both assumptions satisfied. Now we have to fix an antilinear function in W star, which basically will be the right-hand side of our weak formulation, the part which involve the datum F. So we fix W, for every W we associate the integral between 0 and T of this duality product, where F is the function in L2 with the value in V star, so this everything makes sense. And here, just using the Cauchy-Schwarz inequality, we can prove the boundedness of this functional, but in particular the norm of this functional in W star is bounded by the norm of the datum F in the space L2 with value in V star. This will be important to obtain the a priori bound that this result gives us. Because now we are in we are in the setting of the Lyon's theorem, and we can say that there exists a U in the curve V space, so L2 with value in V, such that this is true, this is satisfied for every W in curve W. But this inequality is exactly this integral equation, and this is by the weak formulation, we say that it's equivalent to say that U is in L2 with value in V and H1 with W in V star, and this is a solution of this problem. And the Lyon representation theorem also gives us that the norm of U is bounded by the norm of the capital L in W star, but we say by construction that the norm of W star, the L in W star is bounded by the norm of F. So taking together these two inequality, we have that the norm of U, so the solution, is bounded by the norm of L, it is bounded by the norm of F. So basically the norm of the solution is bounded by the norm of the datum F. Here we present only the existence part, but also the uniqueness part is true, but it's involved other theorem, and so we just focus on this and the application of Lyon's theorem, representation theorem. So after that, I think Azam will show you that if we restrict to a small space H, this cannot be true, and she will show you why.
I will introduce a little notation first. Given two Hilbert spaces, I will denote the maximal regularity of two Hilbert space X and Y to be this intersection. H1 in the bigger space and to be L2 in the smaller. Somehow better regularity means less regularity in time and more so. So where Y is embedded in X. I will make use of it later. Okay, so far what we learned, we just learned that for all F in L2 for some positive T, V prime, there exists a unique U such that it solves the following Cauchy problem, yes? I'm using exactly the same notation that was introduced. And for the sake of simplicity, I will put the initial condition 0. But as was explained, it could be in H. But the question which might arise is that let F not be in the bigger, in V prime. If I put F in H, is it true that, does it imply that U is H1 in H? And the answer is no. Claim, there exists F for the, again, for the sake of simplicity, this T will be chosen to be 2 later. Let me put it to in H such that U has maximal regularity on the whole interval in V prime, but U is not, does not enjoy such a property in H. And the proof, okay, I will prove it, but the idea is to construct a non-autonomous form in such a way that it has different behavior for different, it has different behavior for different time interval. I will make use of what was introduced through notation. I will not erase. But can I have it this one? Which one is? I will come back to the proof, but I need some preparation first. The idea is the following. There exists Hilbert space V embedded densely in another Hilbert space H, and a bounded coercive form, let us call it B on H, on V, sorry. And then again, I will denote the associated operator B, which is a bounded operator between V and V prime. Its part on H, no problem. Its part in H will be denoted by B. But what is important about this form, which is non-symmetric, by the way, it is very important, non-symmetric. What is important about the existence of such a Hilbert space and such a form is that the domain of a square root of B is not included in V. And you have already have the definition of a square root, yes, over there. It was interpolation space, or it could be seen as a complete interpolation space, okay. As I mentioned, it is non-symmetric. Using this non-symmetric form, I can just pay attention, I can restrict my attention to the symmetric part. I will define another autonomous form, which is bounded, coercive. I will denote it by a small c. Again, on V, it is bounded, coercive, defined by, I will restrict my attention to the symmetric part of non-symmetric form B. Okay, by construct, I mean, it follows that because it's symmetric. V is exactly the domain of the square root of C. It is important. And also it is important that I will make use of these two facts. And right now I can construct another form which is non-autonomous. Define the non-autonomous form. Let us call it A. For the sake of simplicity, again, I will restrict my attention to the interval between 0 and 2 on V. I will denote the associated operator, which is bounded by curly A, sorry. And by construction, you can see that A is the same as curly B for the time interval. Sorry, I didn't introduce, I was very quick. I told you that this A has something to do with these two autonomous forms, but I didn't introduce. It's given by, okay, define this by A will be the same as form B for the time between 0 and 1, open, and it will be the same as, it will coincide with the symmetric form C for time between 1 and 2. And then using this, it is easy that, maybe, yeah, this A will be the same as curly B for the time between 0 and 1, and this will be the same as C. Okay, so far so good. Then I will go to provide you with the proof of, where is it gone? I think it is good. Okay, I think it's good. Okay, good. Okay, right now I'm going to show how to show this claim. Yeah. Let U1 be in the domain of a square root of B. B was in, I think you can see there, yes? It is the part of curly B in H, but it is not in V. And also you can see over there that V was the domain of a square root of C. By trace theorem over here, there exists psi in the maximal regularity of time interval between 0 and 2 H dB with initial conditions U0 in U1. Because we have this if and only if, yes. Sorry, it is theorem 1 there. But I formulate the Cauchy problem for initial condition 0. I think during the first talk we saw that this was Lyon, but let me, I think I wrote it somewhere. Yeah, I put initial condition to be 0. That's why it is not good. I need to just introduce another object to exchange somehow. If I put here, still, sorry, we have maximal regularity in H dB. But the good news is that V0 is 0, V1 is U1. Recall that U1 was not in the domain of the square root of C. It is important. And what I claim? Let f to be here, and let us define such a f. Define ft to be v prime b vt for the time interval between 0 and 1, and to be 0 for 1 and 2. Please observe that f is indeed in L2 of the whole interval, it is 0, yeah? H. Also, it is important also you can say that there exists such a W in the maximal regularity of one interval time between 1 and 2, V prime V, which solves the following Cauchy problem. This curly C was a bounded operator. It was associated with a symmetric form C. I put 0 because I have already chosen f to be 0 here. W at 1 is the same as V at 1. It's the same, it is coincide with U1. And U1 was not in the domain of a square root of C. And then consequently, you can see that, I mean, using this if and only if, this W is not in H1 of H. Okay? And then I have to say what is U. Define UT to be the same as VT for 0 and 1, and to be WT for the interval between 1 and 2. Then it follows that U indeed has maximal regularity on the whole interval in V prime, but, and solves, sorry, I wanted to quick, solves the Cauchy problem that I started. My talk with initial condition 0. However, U is not in H1 of the whole interval in H. Why? Because W is not. And this finishes the proof. I'm done. I mean, the next talk, it will be about when you have a positive result. If you put some more assumption on your form, for example, if you assume that it is Lipschitz continuous, but for the sake of simplicity, he will assume that it is C1. And you will see that you can have a positive result. Yes. But yeah, the price to pay is to have more assumptions.
We've now seen that we can have maximal regularity, well, in the autonomous case, of course. In the non-autonomous case, we've seen in the second talk that we get maximal regularity with the V prime or V star, depending on the notation here. But in the autonomous case, we have H1 of H and not H1 of V star or V prime or whatever. And that's the thing we want in non-autonomous cases as well. And we've just seen that this is not just easily fulfilled. And we've seen a counterexample. And the counterexample was sort of not continuous. So the obvious idea is, well, what about a bit more continuity? And that's exactly what we're going to do. And that's also exactly what is the thing which works. In the title, I said Lipschitz continuous forms. For simplicity, I will assume a bit more and then say how to relax this assumption. So the setting is the following. You know it already, but I'm going to repeat it. We have two Hilbert spaces, V and H. V is densely embedded into H. We have a finite maximal time. And we have a non-autonomous form that satisfies certain conditions. And we will see what these certain conditions are. Well, I hinted at what we need. And as usual, we have our operator A defined by the usual pairing that A of t applied to x paired with y is A of t xy. So it's the same thing as in the previous talks. The theorem we want to prove is the following. It looks very much like the one in the second talk. For initial values u0 in V and right-hand sides f in L2 with values in H, we say that there exists a unique solution, u in the space of maximal regularity, this time L2 with values in V, that's the same as before, intersected with H1 with values in H. So this is the main difference. We don't have V star, we have H here. And then this is a solution of our problem, the usual one. And we get a norm estimate, which you should expect. I won't concentrate too much on that one. You do a few computations and you'll get there. I will concentrate on the proof of existence and uniqueness. And well, uniqueness, if you've been following very closely, you will see, okay, that's not very hard. We had Lyon's theorem, and there we have almost everything. For Lyon's theorem, A needs to fulfill 4 assumptions. That's sesquilinearity, measurability, boundedness, and coerciveness. We need that again because we want to apply Lyon's theorem, so we assume A to fulfill all that. Then we get a unique solution in L2 intersected with H1, but V star here. V star is larger, so we still get a uniqueness, but we have to think about existence. And what we're going to do is assume 2 more things. On A, we assume this. We assume that A is in C1, and we assume that A is symmetric. And we'll see in the next slides why this is what we need. We come to existence. The main tool is again Lyon's representation theorem, but this time we will use it a bit differently. I mean, again, there's only one way to really use it, but we use a different form. I will concentrate on the no, that was the wrong slide, wrong button, yeah. I will concentrate on the construction of V, W, E, and L. I will not concentrate on the fact that E is in V star in the first component and that L is in W star, because that's going to be obvious. I will concentrate on the construction and the coercivity, and on the fact that U, this U that we get, will indeed be a solution of our problem. So first thing, the definitions, how to define V, W, E, and L. Well, V is the space this U will be in the end, and U is supposed to be our solution. So V must be our space of maximal regularity, L2 with values in V intersected with H1 with values in H. We need U of 0 to be in V. Yes, this is what we need. So we take a sort of canonical norm. We take something such that U is in H1, that is the H norm of U prime squared, and then integrate it over T. And for the L2 part, we take the V norm of U squared, integrated over T. And then we add the A of 0, U of 0, U of 0 to make sure that U of 0 is actually in V. For E, you usually say, okay, I take my differential equation, I look at the weak form, and use that. So that would be this. That's the weak formulation of the left side of the equation. But we already know we need to show coercivity. That means we need to estimate E of W against the V norm of W. So we take a look at the V norm, and we get the H norm of UW squared. We have a W prime here, but we would like another prime over here to make sure that this estimate is easy. Then we look at the second term. We need to estimate A. How do we estimate A? We know from Lyon's theorem that A must be coercive, so we can estimate the real part. How to get there? We will see in the proof that it's a good idea to look at the derivative of A, because we somewhere need continuity or regularity, and we will use it there. If you just think about it, if you take the derivative of A with respect to T, then you get an outer derivative and twice an inner derivative. If you know what, so we get the outer derivative A prime of stuff, and we get an inner derivative in the first component and in the second component. But if we assume symmetry, we can reorder this and always have it in the second component. And this is what we're going to do. We put a prime here, And on the next slides, if you didn't quite follow why, you'll see this prime is for the differentiability. Then we have two estimates, the first one here and the second one here. We will get different constants. So we will, at this term, e to the minus gamma t, gamma is some constant, real, and we will choose gamma such that all other constants even out nicely and everything works out. I already told you we will differentiate a, then we have the integral over the derivative. That sounds like we're going to use the fundamental theorem of calculus, and they will pop up this term, and we already need to write it down here because otherwise we can't handle it. Yeah, that will be e. For L, we do the same thing. We take the right-hand side of our equation and add our e term and our initial term for the same reasons. So what is W going to look like? What do we need? We need our elements from W to be differentiable, so we need H1. And we need to plug our elements of W into the form, so we need W to be H1 with values in V. And because, oh, sorry, that was too fast. We take the same norm as V because, yeah, it works, and we don't have to overcomplicate things. So we have constructed these things. We need to make sure this U will be a solution, and we can, this is actually coercive. U is a solution. Well, we use what Leo's representation theorem tells us. E of UW is L of W. We choose W smartly, and then everything works out. W will be any element x in V multiplied with a constant. This constant is an integral over some test function. And if we then write down E and L, we get this long term. 3 integrals equal, so the integrands must be equal almost everywhere for every x. That's this one. And then the fundamental theorem of the calculus of variation tells us that if all these forms are equal, then for almost every t, our equation must hold. So U is indeed a solution if we can apply Lyon's representation theorem. So we need to check coercivity. Here I've written down the assumptions, the additional assumptions on A again. We have the assumptions from Lyon's theorem, and now continuity, differentiability, and the bounded derivative of A. And we have symmetry of A. That is, if we switch the space variables, we get a complex conjugate. So if we have that, we can do the following. We need to differentiate our A term, and because in the form we always have this exponential term too, we're going to differentiate it too. And we get a derivative of the exponential term. We get the outer derivative of A, and twice the inner one where we already used symmetry, so we get twice the real part with the derivative in the second term. And now we can use those two new assumptions. We say, okay, we can estimate A by coercivity of A. That was the assumption for Lyon's theorem already. There's a minus in front, so it gets larger. We can estimate A prime because we assumed a bounded derivative, and we just keep the third term. Reordering all this gives us an estimate of the real part of A from below. And this is the main estimate we need for coercivity. I mean, basically that's the estimate we need to do. Now we just plug it in. This was the real part of E of WW. We plug in our estimate of the real part. No? We plug in the estimate of the real part, get this long thing, and here we get from the first term the integral over the derivative. That's the fundamental theorem of calculus. Plug it in. We get an ugly constant here, but we can choose gamma. We choose gamma that the constant is not as ugly and looks more like the other ones, so we put a half here. And now everyone has forgotten the norm of curly V. What was that again? If you remember, this is mostly the norm of curly V. Yeah, I mean, there was the H norm squared, there was the V norm squared, there was this A of 0, which is still there. and yeah, that's it. If you've been following very closely, you might have wondered, well, there was this term and suddenly there's 1/2 of this term. Well, we need this for the 1/2 here, but there's still, I mean, there's still some space in the proof. So space in the proof means we can generalize the proof, and that's the case. We can say, okay, A is not just A, but A is some form A1 plus B. A is the form as before, meaning it's continuous and bounded and whatever. And B is some sort of perturbation, meaning that it's not too bad. Not too bad means I can estimate it, similarly to the one before. But the difference here is we have the H norm here. That's a bit stronger. And this H norm is exactly going to pop up here. We have an H norm and this superfluous looking estimate here, 1 against 1/2, and we plug it in there and everything works out nicely. It's just the same proof. And I already told you in the title, we can assume A to be only Lipschitz continuous. What does Lipschitz continuity mean? If we take the same x and y but different times, we can estimate the difference against some t minus s times the norms of x and y. Then of course we can't do the trick with differentiating A because we can't differentiate it, but in fact we can, meaning we just need the chain rule. That's the thing we used, and we can show that there is another form. If A is only Lipschitz continuous, we can show, okay, there's another form, let's call it, well, A prime, and A prime is just takes the role of the derivative of A. So in fact we can take Lipschitz continuity here. Yes, I've heard last evening that you can generalize this proof even further, that we don't actually need symmetry of A, but sort of symmetry of A, but I won't go into that here because first of all I only learned about this last evening, and second it probably involves a lot of tedious calculations and probably doesn't change the main argument of the proof, at least that's what I hope. Yes, now I think I was faster than expected. But now the final part is Wolfgang with a few outlooks.
Well, I will give a little resume. Many thanks. I mean, so how did it start? Well, in the center is this theorem of Lyon's. I mean, first Manuel, he told us this theorem in the autonomous case. So in the case where we have a semigroup, or where no time dependence, we have no time dependence. Now let's look at it, at this theorem again. So we have a Gelfand triple. This space is injected into H, and then by the usual identification, H is in V prime. So V prime is the biggest space, and the smallest space is V. In applications, V will be a Sobolev space. H will be a L2 space, and this is a dual somehow of V prime, whatever. We have a sesquilinear form, which depends on time, which is bounded. So it's a continuous sesquilinear form as if we fix a T, and it is coercive. This is written here. It's coercive. This means the real part of A T V is larger or equal than alpha V square. And then the assertion of Lyon's theorem is whenever F is an L2 with values in the big space V prime, then we have a solution which is L2 in the small spaces, in the smallest space, and the derivative has its values only in V prime. It solves the equation U prime plus A of t, U of t, F of t, U of 0 equal U0. So Vincenzo gave the proof of this theorem, and if you want to remember something, it was just an application of a Ries representation theorem, which is a little bit different than the Lax-Milgram theorem, because we don't need that one of the spaces is complete. This was a trick. And this is Lyon's representation theorem. So it's a Ries representation theorem. So a very elegant proof, actually. And the theorem, well, I like it a lot because there are many, or several other theorems on non-autonomous equations, but they have quite complicated hypotheses in general. There's one by Kato, there's one by Tanabe, and also if the domain is independent, then there one can also say something. But this is a very, very nice theorem. But as Manuel explained, this operator, curly t, well, it goes from v to v prime. And in our example, we saw, well, we don't really see what this operator does. The right operator is the operator, the part of the operator in H. So there's Lyon's problem. Lyon's problem is what is happening if our f has its values in H, and also let's take u0 in V, and then there is the question, do we find a solution with values in H?
But it's not the V. This, the V prime you replace it by H, not the V.
Oh yeah. Ah, this was a little test. Okay, so V, and here we want, no, what did we want? U is, yeah, exactly. Thank you very much. So we want this. Okay, so this is not a theorem, because Azam, she showed us this is just not true. And she gave an example of a form which was actually a step function. On the interval 0, 1, it was constant, and on the interval 1, 2, it was also constant. And it depended on McIntosh's counterexample, a counterexample for the square root property. We took an operator which has not the square root property. Now the question is this theorem, so we say, I mean, regularity in H, maximal regularity in H, when is this true? And it is true if A is in addition symmetric and C1. So each orbit, so A of T, V, W in T is continuous. I mean, is continuously differentiable. And then the theorem is true. So then there exists a unit U, the derivative is an L2 of H, verifying this equation. Now, what does this mean? I think I can continue here. Pardon?
Das Video kann es nicht aufnehmen.
Okay. So what does this mean? So we look at this equation again. So we have AT U of t is equal to U dot of t minus U dot of t plus f of t. And this now, as a consequence, is in H almost everywhere, because U dot is in H almost everywhere with respect to t. But by our definition of the operator normal A, or you call it script A, this means this is in the part of the operator in H, and of course AT U of t, this is the same as AT U of t. So we have a solution of the equation u dot of t plus a of t u of t is equal to f of t. And this is actually the right equation we are looking for. Let's look at the example Manuel gave us. So let's look again at this example. So in the example, there was H was a space L2 of 0, 1. V is a space H1 of 0, 1, which is injected into H. The form was given by an element. M was in C1 with respect to time and with respect to space. The function should be larger than some delta, and of course it's bounded because it's continuous, so this is smaller than 1 over delta. The form was given by AT. Now, VW equal to integral 0, 1 m of tx u prime v prime of x w prime of x. Well, I should make a bar if it's complex. So, but we take the m real to simplify. And then we have seen the operator a of t, so this is this normal a of t, has domain the functions, say, u in H2 of 0, 1, such that the derivative, the normal derivative, is equal to 0. So H2 consists of functions in C1 on the closed interval. So this has a sense. So this is always in C1, 0, 1. Now, and the operator a of t applied to such a u is minus m of t ux, I mean u prime prime. This is the operator. Now, what does this result tell us now? It says the following. So as a result, we have now the following. So a result which is a consequence of Henning's theorem, the theorem Henning presented. Let f be in L2 now with respect to time and with respect to space. Let u0 be in H1 of 0, 1. Then there exists a unique function u, and this is now in H1 0 time with values in H1, with values in L2 of 0, 1, which is also in L2 with values in V prime, with values in V. And which solves this following equation. So ut with respect to time is equal to m of tx ux tx derivative with respect to time, so we have twice the derivative, plus f of tx. We have Neumann boundary conditions, so ut derivative with respect to x is equal to ut, derivative with respect to x is equal to 0, so this Neumann boundary conditions. And finally, we have the initial value. This is u0 of x. So we solved this parabolic problem, which depends on time. Let me just add two results. Much more is known on this Lyon's problem. I could tell you a series of results, recent results. But maybe abstractly, the problem is completely cleared on the C alpha scale. Spina and Uabaz, they showed, well, the result remains true if this function is merely C gamma, so in the Sobolev space, for gamma larger than a half. So it suffices, instead of continuously differentiable, C gamma suffices to have maximal regularity in H. On the other hand, Fakler gave a counter example and shows H maximal regularity fails if A is merely in C and a half. So gamma larger than the half suffices, but gamma equal to a half does not suffice. So this is really sharp. The result is really sharp. And in addition, now you see, you could think, in view of the example by Azam, that if you have the Kato property, the square root property, then it works. It is not true. Fakler's example is A is symmetric. So if we have a symmetric form, then we always have the Kato square root property. But it does not suffice for this book. So somehow it's disappointing, but it is, the world is made like this. Now, there's a last thing you may ask you after you followed this course on Kato square root property. We know there's McIntosh's counterexample. Okay, this is an abstract form. But what about elliptic operators? We have elliptic operators. It might be like as for Kato's square root property, that the thing is true for elliptic operators, and this would be fantastic. Okay, there is a very recent paper. There's a very recent paper by Sebastian Bechtel, who is here. And then there is Mooney and Marc Ferrar. And this is just in the archive. And it shows maximal regularity fails for AT VW equal by such an elliptic expression as we know them very well by the course. And these are complex coefficients, strictly elliptic, so it fails in such a case. So it's disappointing. We have not the same situation as for the Kato square root property. But they assume that D is larger or equal than 2, and that counterexample seems not to work for D equal to 1. Now, you see, one might look at nonlinear problems. you see, I might change this a little bit and put here m of utx. This is a quasi-linear problem. Now the m is different. The m is just a function from, well, say from R to delta minus delta, and say continuous. So this is composition now. We have a composition now. Now again, we can use Lyon's theorem. And while by some nonlinear strategy, we find a solution. There is a fixed point argument, and we find a solution, but our solution will be only with values in H, and here we have this V prime. But we would like to have a solution, well, of the entire problem, so we would need the result, a positive result, for elliptic operators in dimension 1, and this is still open. Okay, thank you for the attention, and this finished the problem.
Yeah, first of all, thank you for your presentation, and also Wolfgang for making some advertisement for our result. I want to ask a question, but maybe to all of the audience. Namely, as Wolfgang said, there is the case of dimension 1 missing in our result, but there's also a second aspect missing, namely, and this is pretty much the origins of Lyon's questions, he was always thinking about symmetric cases. And our result, as Wolfgang mentioned, it's with complex coefficients, but they are also non-symmetric. So if you want to work on a counterexample in divergence form with maybe complex but symmetric coefficients, would also be very interesting, and I think Wolfgang would also really appreciate if someone can answer this question.
I can confirm this is a good problem. So I take back what I said before. Don't go to the talks anymore. Solve this problem. Are there other questions?
I just have a logistical question. The matches, the box didn't come around. You like this?
No, I didn't like, because I said it's in the last talk before lunch, and this is not yet the last talk, because otherwise you're going to be anonymous in the break. Other questions, please.
Yeah, first I want to also thank you for taking the first presentation on Monday morning, and I thought it was very nice. One thing I didn't really understand now is with theorem 1 we have a relationship between the starting values of the differential equations, and that the starting values in the differential equations are elements of the domain of a squared. I didn't really understand why the domain of a squared is this interesting in the presentation. You talk much about the a square root. Oh yeah, of course. We talked about all these differential equations, and how does that link back to the domain of a square root?
Yeah, first of all, I want to add, I mean, what you said, it was really a big effort. Azam had to leave Poznan in the morning at 3 o'clock, and we were still working in the library at 10 o'clock at night. So it was really big and similar for others. Yeah, well, this square root, this was explained by Manuel, because already in the autonomous case, if you take, then you have a generator of a semigroup. So the function is in, the solution is in h1 of h if and only if this u0 is in the domain of the square root. But the domain of the square root, for all examples, we don't know. You can say the solution of the Kato's problem is to get to know the domain of the square root. It is V this is the whole business. So otherwise the domain of the square root is a miracle. But more generally, you see we have always these mixed spaces, and part of the problem is to get to know these interpolation spaces, because if we have this space here, V prime, and this, then we want to know which are the initial values, because for those, exactly for these initial values you can solve. So it's a problem of interpolation, similar to, which occurs in all contributions to this result. Spinauer, Basu, Fackler also, they also, or we also tried always to find the trace space for the corresponding problem. I hope this answers the question.
Okay, so maybe we skip to the break, and if you have further questions, don't be shy to ask Team Orange in the coffee/fruit break. I should say this was a nice example of a great presentation, but keep in mind there's an award for the best presentations at the end of the week. So maybe you want to keep notes on what you think about the presentation, because the vote is going to be just on Friday after the last talk. Okay, so we thank Team Orange again, and we go to coffee break.